Frequency domain operations. Fourier transform. The frequency concept can be divided into two: temporal frequency and space frequency. Temporal frequency. The temporal frequency is a quantity that measures the number of repetitions per unit of any recurring event. Space frequency. The space frequency describes rate changes of a signal in the space, such as changing the pixel intensities on a picture. Frequency versus wavelength. The frequency is inversely related to the wavelength concept. A higher frequency means shorter wavelength and vice versa. The frequency f is equal to the velocity v of the wave divided by the wavelength lambda. A time domain graph shows the evolution of a signal in the time, while a frequency graph shows the signal components according to frequency that oscillate within a given range. The frequency domain representation helps us to identify noise or unwanted frequencies, which can not be seen so easily in the time domain graph. Once the underside signal components are identified, we can apply various filters to remove them and work only with the signal of interest. Fourier transform. The fast Fourier transform, FFT, provides a method to examine a relationship between the frequency domain terms. Fourier's theorems say that any waveform in the domain can be represented by the cumulative sum of sines and cosines. Then, the same waveform can be represented in the frequency domain as a pair of values of amplitude and frequency phase of each component. The Fourier transform is a mathematical transformation used to convert signals between the time and the frequency domain. It is basically the spectrum or frequency distribution of a function. It is a reversible transformation able to transform any of the other domains. Now, we are going to explain graphically how the time domain transforms to frequency domain with Fourier transform method. The original function, the red one, can be thought of as being amplitude given time. According to Fourier, this function can be constructed with the sum of sines and cosines. Shown here, a simple 6-component approximation of the square wave is decomposed into 6 sine waves. These component frequencies show as very sharp peaks in the frequency domain of the function, shown as the blue graph. These component frequencies show as very sharp peaks in the frequency domain of the function, shown as the blue graph. This new function shows the different frequencies of the original function with their respective amplitudes. And as a result, we get this graph, which is in frequency domain. Images case. In the case of images, the signals in the Fourier spectrum correspond to the gray levels or different intensities in the rows and column pixels of the image matrix. Gradually, varying images have low spatial frequencies. Those with many sharp edges have high spatial frequencies. It is shown a basic example of the frequency domain representation of an image with different levels of intensity. The image can be represented by a sinusoidal left and right image as a sum of signs with different frequency and amplitude. Fourier transform for images. Given an image defined by f of m and n, that is a function of two discrete spatial variables, its two-dimensional Fourier transform 2D TF that is defined as f of m and n that represents the pixel value at row m and column n, and f of omega 1 and omega 2 that is the representation in the frequency domain of f of m and n. Frequency versus distance. High frequencies in the vertical direction cause bright spots away from the center in the vertical direction, and high frequencies in the horizontal direction cause bright spots from the center of the horizontal direction. Therefore, the more distant these points from the center of the image means higher frequency. Filtering. The main objectives for the application of filters are soften the image, remove noise, enhance borders, and detect edges. In the case of frequency filters are applied on an image frequency domain in the Fourier transform. First, the Fourier transform is applied. Then we multiply by the desired filter function. And finally, we apply the inverse Fourier transform. Low-pass filter. Low-pass filter attenuates high frequencies, strong intensity changes, and remains unchanged casualties. In the spatial domain is equivalent to a smoothing filter. The image shows a different cutoff frequencies low-pass filter. High-pass filter. High-pass filter attenuates low frequencies keeping unchanged the high frequencies. These filters provide improved detection of borders in the space domain and reinforce the contrast found in the image. The image shows a different cutoff frequencies high-pass filter. Bandpass filter. Bandpass filter is used to reduce very high or very low frequencies to keep a band mid-range. Just let pass frequencies that are held between two cutoff frequencies.